am going to go over heating curve problems. So I have two problems for you. I should have included heating and cooling curves because I'm doing an example of each, and then in addition to one conceptual problem. So I hope you have gotten a chance to watch the conceptual portion of heating curves. And I'm going to start with this problem, with a heating curve problem. This problem reads, what quantity of energy does it take to convert 0.500 kilograms of ice at negative 20.0 degrees Celsius to steam at 250 degrees Celsius? And you are given the specific heat capacities of ice, liquid water, steam, and then you also are given the enthalpy of fusion and enthalpy of vaporization. For these type of problems, you are expected to draw the heating curve on your own and then apply the um, different calculations to each step. So you have to discern between using Q equals to MCAT versus Q equals to N times enthalpy of fusion or vaporization. So I'm going to start by drawing out the heating curve right here. So I have here on the y-axis is a temperature in degrees Celsius, and I have here is the heat added in kilojoules. Okay. And in this case, it says I am starting from negative 20. So, of course, this is not going to be drawn to scale, but I'm trying my best. So here is negative 20. So and this substance here clearly is water. Now, we need to be mindful. Water has a melting point of 0 degrees Celsius, okay, and a boiling point of 100 degrees Celsius. Note that for other substances other than water, you will be given the melting and the boiling point, but because water has known melting and boiling points, you're not given that information in the question. So I will increase, or I will draw a slanting line to show the increase in temperature, and I will stop at 0 degrees Celsius because this is the melting point of ice. And in this case, after all the heat is absorbed and it reached 0, I will draw a tiny plateau, and this plateau will indicate that there is a phase change occurring. And after the phase change, I will go from 0, okay, to 100 degrees Celsius. So this right here is 100 degree Celsius. Okay, and then I will have a phase change, and this phase change right here, note is the line is a little bit longer because I am diminishing all the intermolecular forces between the water molecules to convert it to a gas. And finally, I can say here, this is at 250. I'm heating the gas or the steam till 250. All right. And to make it easier for you, I can say that this is here ice. This is liquid water. And this is here is steam. Okay, and here I can say that this is melting, and this is here vaporization. Excuse me. Now, with each of these lines, there is amount of heat that's going to be associated with it. So I can label them as Q1, Q2, Q3. Oh, sorry, missed one Q. So Q1, Q2, Q3, Q4, and then Q5. Okay, so let's start with Q1. For Q1 right here, I can say that when heat is added to the substance, it depends on the mass times the specific heat, and the specific heat here of ice times the change in temperature. So I can say that it is 0.500 kilograms. Now note that the specific heat is given in joules per grams degree Celsius. So I can say that it's 0.500 kilograms times 1,000 grams in 1 kilogram times the specific heat of ice, which is 2.03 joules over gram degree Celsius times the temperature. The change in temperature now is, we started at -20, we ended up at 0, so it's final, which is 0 minus 20.0. Now note that this 0, any number that you make up, these two are exact numbers when we're dealing with sig figs. And we have here, the answer is going to be 2,300 joules. All right, and then let's count our sig figs. We have 3 sig figs, and I like personally to change it to kilojoules. It will be usually given to you in the question, so I can see here what amount of energy in kilojoules, and I will just divide it by 1,000, and it will be 20.3 kilojoules. Now for Q2, Q2 is a plateau. It means that this is a phase change. So in this case, I'm going to use, and we're melting. So this is melting or fusion. So N times enthalpy of fusion. Since we don't have N, we only have the mass. So I'm going to convert to, or divide by, the molar mass of water. Okay, and then I'm going to multiply by the enthalpy of fusion, which is 6.02 kilojoules per mole. And this is going to give me 167.036626 kilojoules. Again, let's look at our sig figs. 3 sig figs, 4, and then 3. So it's going to be 3 sig figs. Now let's see here Q3. Q3 is, we're increasing the temperature. So Q times, Q. It's M, mass, times, now the specific heat, we're liquid water. So here is going to be liquid water times delta T. So it's going to be the 0.500 kilograms, 1,000 grams over 1 kilogram, times, here liquid water is 4.18 joules over gram degree Celsius. And if you're wondering, we're including the sig figs of specific heat capacity, since this is a measured value, times delta T. Now it's going to be from 0 to 100 degrees Celsius. So 100 minus 0 degrees Celsius. And it's going to be Again, this is 3 sig figs. 3 sig figs, these are infinite, so 3 sig figs. So it's going to be 209,000 joules. And then I'm going to switch to kilojoules. And this is going to be 209 kilojoules. I am going to continue on the next slide. I'm just going to okay, and I'm going to continue with the Q4. Q4 right here. This represents a phase change vaporization. So I'm going to use N times enthalpy of vaporization, and this is going to be the 0.500 kilograms, and then 1,000 grams over 1 kilogram times, I'm going to divide by the molar mass of water, 1 mole H2O over 18.02 grams H2O, times 40.7 kilojoules per mole, which is given to me right here. And again, 3 sig figs, 3 sig figs, 3 sig figs, which is going to be this number is going to be 1129.3 0.00777 kilojoules. And if this is 3 sig figs, and then finally, I am going to do Q5. Q5 right here, we're heating the steam. So M times C, steam times delta T, and this is going to be 0.500 times 1,000 grams over 1 kilogram times the specific heat of steam, which is 2.02 joules over grams degrees Celsius. Always be mindful of your units. And this right here times delta T. Delta T here, we are going from 100 to 250. Okay, so it's going to be 250.0 minus 100 degrees Celsius. And this also right here, the lowest amount of sig figs is going to be 3 sig figs. And this is going to give me 151,500 joules. And then I'm going to change to kilojoules, and this is going to give me 151.5 kilojoules, and there is 3 sig figs. Now, what really we want to do is we want to do the Q total, or the quantity of energy. So I can say here, Q total is going to be Q1 plus Q2 plus Q3 plus Q4 plus Q5. And in this case, to show you how I'm going to obtain the sig figs, I'm going to stack them up on each other because we're doing here addition. So be careful with this type of problems because we're doing multiple operations. And I'm going to start with the 20.3 kilojoules. This is Q1 plus the 167.0. So let me highlight the sig fig so we don't get lost. Here. So it's going to be 167.0 0.03 6626. Let me remove the kilojoules so it doesn't throw you off. And plus D, and the sig figs here were here. Okay. And then we have here 209 kilojoules. And then we have 9211. Okay. And oh, ooh, okay, and the sig figs are here on day 10's place. And finally, we have the um, final one, which is the Q5, which is 151.5, and it's right here. Okay, now since we are adding all these together, I can just draw my line right here because we incorporate the lowest number of sig figs, and the lowest number of sig figs will be the 1,677. So here will be the tens place. So in this case, the Q total will be 1,677 kilojoules. And I'm gonna round it up. So it's gonna be 1,680 kilojoules. I hope this was clear enough. And I will be doing a different problem since this video is a little bit long, a different problem in a different video regarding cooling curves.